Hello and welcome again to my physics video lecture supplement series. In today's video I want to talk a little bit about a centrifuge, and so today is basically an example of rotational motion in which we calculate the centripetal force and the centripetal acceleration experienced by an object inside of a centrifuge. And basically, we're doing this because a lot of students who are taking my physics classes are either bio majors or life science majors in general, or else they're pre-med students. And a centrifuge is actually one of the major tools of the trade for microbiology, especially cell biologists, and then also for medicine. They're used in hospitals around the country to basically examine blood samples, examine urine samples, etc. Basically, you place a blood sample into this centrifuge, you put it in a test tube, it spins the test tube around very quickly, and it can separate out, for example, the larger, heavier parts of blood, such as the red blood cells, from the lighter part of the blood, namely the plasma, the fluids. And for what it's worth, everybody who has a washing machine at home also has a centrifuge in their household, because a washing machine is basically a large centrifuge. And it basically, when it's time to dry the clothing out, the first stage is the very rapid spin in the washing machine, in which basically the water is separated out from the rest of the laundry and sort of drains out. So you pull out damp but not necessarily totally soaked clothing that you can then stick in the dryer and get dry in a reasonable amount of time. So today's example, I wanted to look at a simple centrifuge that basically looks like a basin that has an inner and an outer radius. So the inner radius is 10 centimeters, the outer is 15. So the fluid that you decide to put into the centrifuge is sitting in this region here, in between the two lines. And we want to know what's the difference in centripetal acceleration from the inner to the outer part of the centrifuge, and what's the difference in centripetal force given two different particle masses? And how does the centripetal acceleration, and therefore the centripetal force, compare to gravitational acceleration, and therefore the weight of the object? So the centrifuge, let's say, spins at 450 revolutions per second. That's comparable, maybe a little on the fast side, for a simple ultracentrifuge. And so the first thing that we've got to do, we want to find the centripetal force. So centripetal force is going to be object mass times centripetal acceleration. And the centripetal acceleration, in turn, is going to be the object's tangential speed squared divided by the radius from where the object is to where the center of this spinning motion is. And this tangential speed is basically equivalent to saying, you know, the particle at this point in the circle has a velocity that is so fast and moving tangential to the circle. So this tangential speed is the how fast part of it. It's basically a translational speed, but it's the velocity itself is shifting as it goes around the circle. And this tangential velocity is always going to be r times omega. So we have r omega squared over r, and so we need to know the radius times the speed squared, the rotational speed squared. So we're given some initial and constant rate of revolution. So this is, we'll call this revolution rate, and the angular speed is going to be this revolution rate converted into radians per second. So each revolution is 2 pi radians. So we need to have 2 pi times the revolution rate. And so that means that this angular speed is approximately 2,830 radians per second. Okay, so now we can plug that in for our acceleration into the omega to figure out what is our acceleration at inner and outer edges. So for the inner edge, ACI is going to be, R is 10 centimeters, so it's going to be 0.1 meter times this rotational speed. So that's actually approximately 7.99 times 10 to the 5th. Meters per second squared. Sorry, the rotational speed should be squared. So how many times g is that? Well, g is approximately 9.8 meters per second squared. So we should divide this acceleration that we obtained by 9.8 meters per second squared. And when you do that, you end up getting approximately 8.1 times 10 to the 4 times g. And you'll notice that this last one is 2 significant figures. We only had 2 significant figures in the radius, so we should express it as 8.1 times 10 to the 4 g. Okay, so that answers part of the first question. The other is, what about the outer one? So 0.15 meters instead of 0.10 meters times 2830 radians per second quantity squared. And that's going to give us approximately 1.2 times 10 to the 6th meters per second squared. So that's the actual centripetal acceleration. Now, if I wanted to know the number of g's that is, again, divide by 9.80. And so this is approximately 1.2 times 10 to the 5th g's. Okay, so that fully answers the first question. Basically, it means that no matter what object you have, if it's on the outer edge of this thing that's spinning at 450 revolutions per second, the outer edge is 15 centimeters, then the centripetal force will be 120,000 times the weight of the object. And on the inner edge, it'll be 81,000 times the weight of the object. So that's a lot of force. So what's the difference in force for some object of known mass? We'll use the 0.1 milligram. Well, 0.1 milligram, so long as we're going to do this in newtons, is equal to 1 times 10 to the negative 7 kilograms. So if you wanted to use newtons, we should put it in kilograms. If you want to use dynes, we should at least convert it to grams. 100,000 dynes, 1 newton. So for the inner edge, we have that the force is going to be 7.99 times 10 to the 15 meters per second squared times this mass. So on the inner edge, the force on this 0.1 milligram object is going to be 0.1199 newtons. And for the outer edge, we use the acceleration at the outer edge, 1.20 times 10 to the 6th meters per second squared. And again, same mass, 1.0 times 10 to the minus 7 kilograms. Okay, so the total force then for this same object on the outer edge is going to be approximately 1199 newtons. Sorry, I wrote the wrong force down up here. It should actually be 0.0799. My apologies for that. So if you want to find the difference in force, you subtract the inner from the outer. So let's go ahead and erase some of this. Difference in force, therefore, delta F for object 1 with mass 0.1 milligram is going to be Fc outer minus Fc inner for 1. So 0.1199 minus 0.0799 newtons. So what you end up with is that the difference in force is approximately 0.040 newtons. And that's the difference in force experienced by a 0.1 milligram object between the inner edge and the outer edge. Okay. So if we wanted to know for the smaller object, the one that's only 0.01 milligrams, all the process is the same, and in fact, all the numbers are the same. We just replace these masses by 1 times 10 to the minus 8 kilograms instead of 10 to the minus 7 kilograms. And so for object 1, it was 0.04 newtons. For object 2, you end up getting a difference of force of 0.004 newtons. Okay, so that is how much force, difference in force the object experiences when it moves from inner edge to outer edge. And that's what we've got time for today. Hope you enjoyed this video, and thanks for watching. So farewell.